We turn now to the case of a strong base and a weak acid. And now the situation gets more interesting because we have to take into account the equilibrium behavior of that weak acid and its conjugate base. So let's write the reaction down. Let's take our favorite acid, acetic acid, CH3COOH, and let's react that with water. And in that weak acid reaction, we produce the acetate anion and we produce an H3O plus. That is the reason for the acidity of that combination. Now the acid equilibrium constant for this reaction is 1.76 times 10 to the minus 5. And as soon as we see that equilibrium constant, we realize that this is a weak acid because 1.8 roughly times 10 to the minus 5 is a very small number. That means that a very small fraction of that acetic acid has dissociated. Now, if we're going to add to this combination a strong base, that introduces the hydroxide anion. And we can do that by simply adding sodium hydroxide to the mix. So let's just write down that reaction in water that gives us the sodium cation and the hydroxide anion. But as soon as we see a hydroxide anion produced on the right-hand side of that equation, we realize something immediately, and that is that that H3O plus that came from the acid reaction is going to react immediately with hydroxide anion. So we've now developed what we might term our favorite reaction, the neutralization reaction, which is H3O plus reacting with OH minus to form two molecules of water. But here's the interesting thing. Because the equilibrium constant for water, the reverse reaction, so if I want to write H2O going to H3O plus plus OH minus, that is the dissociation constant for water. That's 1 times 10 to the minus 14. But now we know we can calculate the equilibrium constant for H3O plus OH minus because it's just the inverse of the equilibrium constant for the reverse reaction. So that means that the equilibrium constant for this reaction is equal to 1 over the equilibrium constant for water, Kw, and that is 1 over 1 times 10 to the minus 14, or 1 times 10 to the plus 14, as we looked at before. But when we add this to our initial weak acid reaction, we come up with another reaction. That is, we have CH3COOH, that's our original weak acid, but now it reacts with the OH minus that we've added to the solution, and that produces the anion, which is the acetate anion, plus water. But now the equilibrium constant for that is equal to the acid equilibrium constant times 1 over Kw, and that equals a large number, which we'll look at in just a moment. This is just what Le Chatelier would tell us. The equilibrium shifts to the right. And the equilibrium shifts to the right because of the reaction of the OH minus coming out of the added base reacting with H3O plus. And we can calculate this new equilibrium constant. That's Ka, the acid dissociation constant, times 1 over the dissociation constant of water. And that's equal to 1.76 times 10 to the minus 5 divided by 1 times 10 to the minus 14. And as soon as we see that 10 to the minus 14, we know that that's going to be a large number. That turns out to give us a quantity of 1.8 times 10 to the 9, an extremely large equilibrium constant. But we also know something else. That's the equilibrium constant for this reaction, the reaction of the acid with the added base. And so we can write down in terms of the concentrations exactly what that equilibrium constant refers to, because the product of that reaction is the acetate anion CH3COO minus, and water is the other product, so pure water, of course, drops out of the equilibrium expression. And in the denominator, we have the acetic acid concentration and the hydroxide anion concentration. But this is a remarkable result. And so let's go back to our graphical representation of exactly what's happened here. This is spontaneous. That means that delta G is less than 0, and it proceeds from left to right. So let's begin again by looking graphically at what we have. We have a weak acid, and that means that we've got a lot of the acid in with our H3O plus, and we have much more acid than we have H3O plus, which simply means it's a weak acid. So we have a weak acid, and to that we add our strong base. Now, the strong base means that before the reaction has taken place, we have a whole lot of OH minus floating around in solution, along with the Na plus cation that brought that base into the solution. Now we mix them together, but before the reaction has gone to completion, we recognize that every OH minus is going to find an H3O plus in that solution. And as the reaction progresses, each one of those H3O plus OH minus is going to form 2 water molecules. And of course, those water molecules simply disappear into the background. They're the same as everything else in solution, and water is in vast excess over any of these other reagents. So the result of the reaction is that we end up with an equilibrium, and that equilibrium represents the reaction of the acetate anion, that's CH3COO, reacting with water to form CH3COOH, the weak acid, plus OH minus. All right, so now we've tracked through from the initial conditions to the final condition.